Alright, assalamu alaikum. So in this video, we will study about two very important applications of reversible reactions. That is, two industrial processes, which give us the end product of those industrial processes are two extremely important chemicals, which form a very important framework of the entire industrial setup. One of those chemicals is the nitrogen-based compound ammonia, and the other is a compound named sulfuric acid. So let's begin. We'll start off with formation of ammonia, right? And formation of ammonia is done by a process called the Haber process. Haber process, it is a process for formation of ammonia. And the name Haber comes about because it was founded by a guy named Fritz Haber, and this discovery was made uh, during the World War II or just slightly before the World War. Right, yeah, it was made slightly before the World War. This guy was German and he made this discovery. He and other guy named Bosch, Bosch. So it's also called, in some books you might see this process written as Haber-Bosch process, giving credit to the other guy as well. Right. So what are the key things in the Haber-Bosch process? Number one, we have the reactants. Now, ammonia has a formula of NH3. So, the reactants for forming ammonia obviously should be a source of nitrogen and a source of hydrogen. So, these are the two reactants that we are concerned with. Right? Number two, we need some temperature requirements. We have some temperature requirements and we have some pressure requirements as well. Then number three, we have a catalyst that's essential for this process to occur. So now, let's talk about the reactants first. The reactants are nitrogen gas and hydrogen gas. How do we obtain each of these two? The answer is that we know that air contains 78% nitrogen. It means that air itself is the biggest possible source of nitrogen that we have available to us. So, what we do is we take air, we cool it down to a very low temperature, that is, we liquefy air, and then we fractionally distill air. Why? When we liquefy air, obviously we are liquefying the nitrogen present in the air, we are liquefying the oxygen present in the air, and we are liquefying all other gases that are present. So what we do is that we have to, because we only need nitrogen, so what we do is that we carry out fractional distillation of liquefied air to give us N2 only. So N2, that is nitrogen gas, is obtained from fractional distillation of liquefied air. Now what about hydrogen? Even though hydrogen is a component of air, but we cannot obtain hydrogen in sufficient quantities from fractional distillation of air. The reason being that we have a very small proportion of hydrogen in the air, and obtaining hydrogen in the air through fractional distillation of air would be an extremely uneconomic and inefficient process. Why? Because we have very small quantities of hydrogen in the air. So instead, hydrogen is obtained through the ground, right? Hydrogen is obtained through fossil fuels. And there are two methods of obtaining hydrogen, both of them involving fossil fuels. One of the methods is known as cracking of hydrocarbons. And the second process involves the reaction with methane. And this a nice name of this reaction. I'll just let you know about the name. Yeah. Steam reforming. In steam reforming, what we do is that we react methane gas with steam in the presence of a catalyst. What is the name of that catalyst? You are not supposed to know at this level. What happens as a result of this reaction is that hydrogens from methane as well as water combine together to give us three molecules of hydrogen gas and one molecule of carbon monoxide. This hydrogen is then used as the raw material for Haber process. Right, so this is about steam reforming. And yeah, another important thing is that this reaction in itself is a reversible reaction. So that means we have to carefully control everything in this reaction as well. Now let's take a look at this reaction. In this reaction, we have methane, which is a gas, we have steam, which is also a gas, and we are getting hydrogen gas and carbon monoxide gas. Now since this is a reversible reaction, and since it has gases on all the sides, what will happen if I increase the pressure of the system? The answer is that increase in pressure favors the side of the decreased number of molecules. So we can see that on the reactant side, we have two molecules. Why? Because there's just one molecule of methane and one molecule of water. Whereas on the product side, we have three molecules of hydrogen and one molecule of carbon monoxide. That is a total of four molecules. So if we increase the pressure of this system, we are gonna get the reactant side as the favored side, and obviously that's not something that we want. So the steam reforming technique of forming hydrogen gas is carried out at a low pressure. Why? Because when we have low pressure, the side with the increased number of molecules is favored, and that is the reactant, and that is the product side, and hydrogen on the product side is what we require. Right, so this is one of the techniques for obtaining hydrogen. The other technique, that is cracking of hydrocarbons, involves. Alright, I'll try to make this as simple as possible because this has got something to do with organic chemistry, and we haven't studied organic chemistry yet. Well, what happens is that there is a special class of organic compounds called hydrocarbons. Hydrocarbons are organic compounds that contain carbon and hydrogen only, right? So we have certain hydrocarbons. See, methane is also a hydrocarbon. Why? Because it's just got one carbon atom, four hydrogen atoms, no other element involved. Right? So it's a hydrocarbon. So what happens is that there are certain hydrocarbons that have extremely long chains of carbon atoms with hydrogen atoms attached to them. So what happens is that these long chain hydrocarbons are of very limited use. So what we try to do is we try to break these long chain hydrocarbons into shorter chain hydrocarbons. The process of breaking down long chain hydrocarbons into short chain hydrocarbons is called cracking. And one of the byproducts of cracking is hydrogen gas, right? So we'll just write this down here. In fact, I'll write underneath, right? So here it is. cracking is a process of converting. Now, this conversion of long chain hydrocarbons to shorter chain hydrocarbon chains is done via a catalyst. So it is a catalytic conversion, right? We'll talk about it in more detail when we study organic chemistry. Right now, we'll just write down that cracking is a process of catalytically converting long chain hydrocarbons to shorter chain hydrocarbons. I'm not discussing any details of this reaction. However, the detail that's important is that hydrogen gas is produced as a byproduct. So now we have obtained the reactants needed for the Haber process to continue, to start, right? That is, we now have our source of nitrogen and we now have our source of hydrogen. But do we need nitrogen and hydrogen in equal quantities? The answer is definitely no. Why? Because we can take a look at the formula of ammonia and we can see that we do not have equal amounts of nitrogen and hydrogen in an ammonia molecule. Instead, we have just one molecule or one atom of nitrogen and three atoms of hydrogen in an ammonia molecule. Therefore, for one volume of nitrogen gas, we need three volumes of hydrogen gas. I hope that this is clear. So now what we do is we pump these gases into this first chamber. And this first chamber, what we do is these gases are scrubbed and are cleaned. Right, right. Why is this important? What kind of cleanliness is carried out? The first thing is that when we pump the gases, some dirt molecules, some other impure gases are bound to come and attach and come in this, are bound to come into the system along with nitrogen and hydrogen gases. Now, if we allow these impure nitrogen and hydrogen gases to move through the system and all the way to this third converting chamber, what would happen is that the converting chamber has beds of catalyst, right? The catalyst that we use is iron, and we use finely divided iron. What do we mean by finely divided iron? Finely divided refers to the fact that the iron used as a catalyst here is actually powdered iron, right? And the reason why we use powdered iron is so that we can have the maximum surface area for the reaction. Because we know from our discussion on rates of reaction that powdered substances have a much higher rate of reaction. Anyway, so what happens is that if we allow impure gases, impure nitrogen and hydrogen to come into the converter, the impurities are gonna attach to the catalyst and they will poison the catalyst, right? And when the catalyst is poisoned as a result of those impurities attaching to the catalyst becomes unsuitable for use in future, which totally destroys the purpose of a catalyst. A catalyst is supposed to speed up chemical reactions by remaining unchanged chemically itself. If the catalyst is poisoned, it means that it would become chemically changed and it won't be able to function as a catalyst effectively anymore. Right? So for this reason, the gases are mixed and scrubbed. And scrubbing is cleaning, which involves removing dust particles or any other impure gases. Right. After the cleaning process is done, the gases are compressed. Why is compression important? The compression is important because it raises the concentration of gases. Why? Compression increases the pressure. This increases pressure, and we know that in gases, increase of pressure is equivalent to increase of concentration. So when we have a higher concentration of nitrogen and hydrogen, it is more likely that the nitrogen-hydrogen molecules would be closer together, and hence it would be easier to make them react with each other. Right. Now what happens is that the compressed gases enter the converter, and in the converter we have two very special conditions. We have a high atmospheric pressure uh, of 200 atmospheres, and we have a high temperature of 450 degrees Celsius. Right? Uh, these gases enter the bed and are exposed to a high pressure and a high temperature. Now, what does this catalyst do is, this catalyst uh, helps the reaction between nitrogen and hydrogen, right? And how does this happen is, I'll just give a very slight detail of the reaction mechanism that is occurring. Let's say that this is a bar of iron. What happens is that we have nitrogen molecules and hydrogen molecules. So each of these molecules approach the surface of the catalyst. When each of them approach the surface of the catalyst, what happens is that the bonds between the nitrogen molecules and the hydrogen molecules weaken and ultimately break. Therefore, every nitrogen atom now has three free valencies, and every hydrogen atom has one free valency. Therefore, what happens is that three hydrogen atoms attach to one nitrogen atom, giving us ammonium. So let's summarize this. What happens is that as nitrogen and hydrogen molecules approach the catalyst, the bonds between the molecules weaken and ultimately break. This breaking of bonds between the molecules themselves causes formation of, uh, not causes, creates three free valencies per nitrogen atom and one free valency per hydrogen atom. Therefore, nitrogen atoms, one nitrogen atom combines with three hydrogen atoms, giving us ammonium. Right. Right. So let's write down the effect of a catalyst on the molecules. As nitrogen and hydrogen molecules approach the catalyst, the bonds between the nitrogen atoms and hydrogen atoms in their respective molecules weaken and ultimately break. This gives us isolated nitrogen and hydrogen atoms which can covalently bond together to form ammonia. However, there's one thing which is extremely important and we must remember this. That is that a catalyst has absolutely no effect on the position of equilibrium, right? So we know that the reaction between nitrogen and hydrogen to give us ammonia is a reversible reaction. So a forward reaction will be taking place as well as a backward reaction. Now the catalyst is basically going to speed up the rates of both the backward and the forward reaction at the same rate. The important thing, however, is that it does this in a lesser amount of time as would have happened without a catalyst. So the important thing here is a catalyst, any catalyst for that matter, does not. There's just one catalyst which in which this does not happen, and we'll study about that catalyst in organic chemistry. A catalyst does not alter the position of equilibrium. It increases the speed of both the backward and forward reactions to the same extent. Right, so this is how a catalyst works. There's some more detail that you'll study about in A levels, but at your level, this is more than enough. Now, let's take a look at the equation uh, for the reaction between ammonia and the reaction between nitrogen and hydrogen. Nitrogen plus 3H2 gives us 2NH3. Remember, if you are ever asked to write the equation for the Haber process, this is the equation that you're going to write. Okay. So in this equation, we can very clearly see that we have two reactants. All of them are gases, and it's a reversible reaction. So if we increase the pressure, then according to the rule that we studied in the video on reversible reactions, we know that increase in pressure favors the side of lesser number of molecules. We can see that on the reactant side, we have a total of 1 and 3, 4 molecules, and on the product side, we have 2 molecules. So an increase in pressure favors the side of the decreased number of molecules, which in this case is the product side. That means increasing pressure favors the forward reaction, and we get more ammonia. And this is the reason why we are using a high pressure of 200 atmospheres. But a catch comes about when we talk about the temperature used. The temperature, as we can see here, is 450 degrees Celsius, which is a pretty high temperature. And the problem is that this 450-degree temperature is fine, but the forward reaction is exothermic. So now what happens is that because the forward reaction is exothermic, that is, the forward reaction increases the temperature of the setup. It means that if we increase the temperature of the setup, the equilibrium is going to shift in a direction which reverses this change, that is, which opposes this increase of temperature. Therefore, the backward reaction is preferred. Why? Because the forward reaction is exothermic, then the backward reaction is definitely going to be endothermic, and since the equilibrium is going to try to reduce the temperature that we rose, the backward reaction, which is endothermic, is preferred because endothermic reactions decrease the temperature. I hope this is very clear. So, this 450-degree temperature, this means that it favors the backward reaction, and that's something that we really don't want. However, it is a necessity to use this high temperature. The reason being that if we take lower temperatures, even though that is gonna increase the yield of ammonia, but it is going to decrease the rate of reaction significantly. Remember in the video on rates of reaction, I told you that there are two separate things that we have to consider. One thing is the rate of reaction, and the other thing is position of equilibrium. Whenever we increase the temperature, the rate of both backward and forward reactions will be increased as well. However, the position of equilibrium is independent of the rate of reaction. And in this case, raising the temperature favors the backward reaction, right? But the problem is that if we decrease the temperature, which would increase the yield of ammonia, the problem is that the rate of reaction would go down a lot, and this would slow down the reaction to uneconomic limits. Why? Because when the reaction becomes slow, you have to run this machinery, this whole expensive process for a very long amount of time. And this long amount of time would mean increased expenses for running the machine, for providing this high pressure, for maintaining this high pressure, for maintaining these high temperatures, for running these compressors and everything. This is gonna require a lot of costs. So the conclusion is that if we take lower temperatures, even though it is going to increase the yield of ammonia, it is going to decrease the rate of reaction to very uneconomical limits. Therefore, the temperature of 450 degrees, even though it is a relatively high temperature, we still have to use this temperature as a compromise temperature, because if we take temperatures any lower than this, we are going to get extremely slow rates of reaction, which is something that we really don't want. So we'll write this down. Just a second. Right. The forward reaction is exothermic. This means that it favors a lower temperature, and increasing temperatures causes the reverse reaction to be favored. However, if we decrease the temperature, the rate of reaction would become uneconomically expensive. That is, the costs involved would would not outweigh the benefits, right? Would become uneconomically expensive, would become uneconomically slow, and the process would become too expensive, since high costs are involved in maintaining the machinery involved, the machine, yeah, the machinery used for the process. For this reason, a temperature of 450 degrees Celsius is used despite being relatively high, as a compromise temperature. That is, even though this temperature produces a relatively lower yield of ammonia, it does so at a at, at an economical rate. Fair enough. So you often get this question in your papers, asking you to describe what do we mean by uh, the term compromise temperature, or you will be asked to explain the effect of this 450-degree temperature on the yield of the reaction and so on. So this is what you're going to write at that point. So I hope this is clear. Now, we have reached up till this point. A lot of ammonia has been formed. See, but the problem is that the yield of this process is pretty low. What do I mean when I say yield? See, in ideal conditions, what should happen is that all the nitrogen and all the hydrogen should be converted to ammonia. In this case, if all nitrogen and all hydrogen is converted to ammonia, we say that the yield of the reaction is 100%. Why? Because 100% of the products are used up, or of the reactants are used up to form the product with no wastage, with no remaining reactant. Right? That's called a 100% yield. And when we studied moles, the chapter of moles, I told you at that point of time that it's not possible. No reaction actually has a 100% yield. Here, however, the yield is a bit too low. The yield is around 15% to 18% only, which means that only 15 to 18% of the nitrogen and hydrogen gases are used up, and only 15 to 18% of the full capacity of ammonia that could be formed from the reactants is actually formed. And this means that 82 to 85% of the nitrogen and hydrogen remain unreacted. And it's for this reason, if you take a look at this diagram, we see that what leaves this converter is nitrogen, hydrogen, and ammonia. This is very significant. And it's for this reason why, if you take a look at this cooler, a pipe is escaping this cooler. And what is in this pipe? Nitrogen and hydrogen gases, which are gonna go back through this pump and into the converter. That means the remaining unreacted nitrogen and hydrogen gases are recycled. Whereas the ammonia which is formed, it goes into the cooler, it is liquefied, and it is removed in tanks. So let's write this down. Different color. Right, so the yield of this process is pretty low. It's around 15 to 18%. This means that 82 to 85% of the nitrogen and ammonia, of the nitrogen and hydrogen, remain unreacted at the end of the converting process. And what leaves the converter is a mixture of nitrogen, hydrogen, and ammonia gases. Ammonia is cooled down and liquefied and removed from the system and stored in tanks. The remaining nitrogen and hydrogen gases are then recycled to give more ammonia in the next process, in the next cycle. And this process continues until all the ammonia, until all the nitrogen and hydrogen are used up. So we have formed ammonia. Fine. Now let's take a look. Of the techniques that we use in this process to speed up the reaction, to uh, to shift the equilibrium in favor of the side that produces ammonia, and so on. So first thing, measures to speed up the reaction. Number one, use of a catalyst, use of the iron catalyst. Number two, use of 450 degrees Celsius temperature as a compromise temperature. Now let's talk about measures to shift the equilibrium to the forward side. Equilibrium in favor of the forward reaction. The first thing that we do is use of a high pressure, that is 200 atmospheres. The second thing that we do to shift the equilibrium in favor of the forward reaction is that we keep removing ammonia that is formed. And how does this shift the equilibrium in favor of the forward reaction? Let's take a look here. What happens is that it's a reversible reaction, right? So what we do is we remove any ammonia that is formed. This means that we are reducing the amount of ammonia here. Now, if we reduce the amount of ammonia, the equilibrium will shift in a direction that increases the concentration of ammonia. Therefore, the forward reaction will be preferred. Right? I hope this is clear. So, the second way in which we shift the equilibrium in favor of the forward reaction is by removing any ammonia formed. So that's all about the Haber process. Ammonia is formed. This ammonia is then sent to the relevant industries where it's used for multiple processes. A vast amount of ammonia, in fact, a vast majority of ammonia is used in making fertilizers. Why do we need ammonia for fertilizers? The answer is that a good fertilizer contains a high content of nitrogen. Nitrogen is basically an essential component of proteins. So the protein synthesis of plants requires a high amount of ammonia, of nitrogen, and the source of nitrogen in fertilizers is generally ammonia. Alright, ammonia is also used to make explosives, right? It's also used to make nitric acid, and we know that nitric acid has a lot of uses as well. So the uses of ammonia are given in your book. You can go through them, and it's pretty easy. So we are done with the Haber process, that is the formation of ammonia. Now let's talk about another process, that is the contact process. And contact process forms sulfuric acid. Contact process, and it is the formation of sulfuric acid. Now before we talk about the contact process, let's talk a bit about the element sulfur. So sulfur is basically a non-metal. It is a brittle yellow solid with a pungent smell. And we have two allotropes of sulfur. What is an allotrope? We have studied about allotropes previously. We'll just review it. An allotrope of any element is a different structural form of that element. For example, if we talk about carbon, carbon has two famous allotropes, namely diamond and graphite. Both of them are completely carbon. They have just carbon atoms, but they have different structures. These two different structures in which the atoms of an element orient themselves are called the allotropes of that element. So sulfur has two allotropes. One of those allotropes is called rhombic. Rhombic sulfur, and the other allotrope is called monoclinic sulfur. I'll show you the pictures of each of these allotropes. Okay, here we go. So this one at the top, it is this nice, beautiful rhombic sulfur, and the one at the bottom is monoclinic sulfur, right? So we can see here, both of these are just sulfur atoms, nothing else in them. But we can see that one has this nice crystalline appearance, it looks really beautiful to the eyes. The other is some pretty ugly stuff. So these are two different structural forms of sulfur. Right. Now sulfur has a low melting point. And its melting point is around 112 to 115 degrees Celsius. And this low melting point has a very important influence on how we extract sulfur from the ground. I'll just tell about that shortly. So, having discussed this, let's talk about how sulfur is extracted from the ground. So, one thing that we need to know is that sulfur is primarily present in the ground in two forms. It is either present in an uncombined form, that is, it is found native in the Earth's crust. And uh, what do we mean when we say that something is found native? It means that it's uncombined with other elements. The second primary method of extracting sulfur is alongside fossil fuels. So, sulfur is a very important impurity in fossil fuels, be it coal, be it crude oil. So, what we do is that in order to because sulfur is an important industrial and environmental pollutant, what we try to do is that we try to remove sulfur from these fossil fuels before we use them. So, when we purify fossil fuels, we get a lot of sulfur from them. So sulfur is obtained from the purification of fossil fuels. The other technique, of course, is that it's present uncombined in the Earth's surface. So what's done is that geologists survey the land and they see that alright, this place contains a nice amount of sulfur. So a small mine is set up in that area, and it's pretty easy to set up a mine for extracting sulfur. Why? Because you just have to identify the area. Let's say this is the area where we have sulfur underneath. So what we'll do is that we will make a hole in this area, and we insert a pipe here, and then obviously there's a return pipe as well. This is the entry pipe, this is the return pipe, and through this pipe we are gonna send underground superheated water. Superheated water is around 120 degrees Celsius. Superheated water under pressure. So superheated water goes under the ground and melts the sulfur that is present underground. Now, when this water moves up again, it is going to carry molten sulfur with it. This molten sulfur is then taken, it's purified, and it's used for whatever purposes we want to use it. So that's how sulfur is extracted from the earth. Now, sulfur reacts readily with oxygen. It produces a blue flame when it burns in oxygen, and it produces sulfur dioxide gas. Right? So, sulfur burns readily in oxygen with a blue flame, forming sulfur dioxide gas. Now, this sulfur dioxide gas is a major environmental pollutant. It's an air pollutant, basically. And sulfur dioxide, which is SO2, it combines with water to form sulfurous acid, H2SO3. Sulfurous acid. Sulfurous acid is a weak acid and it is used for bleaching paper and making it whiter. It is also a component of acid rain. Now, when sulfur dioxide goes in the atmosphere, it goes up in the upper layers of the atmosphere. There, what happens is that we also have oxides of nitrogen. Now, these oxides of nitrogen act as a catalyst and convert sulfur dioxide to sulfur trioxide. And when this sulfur trioxide reacts with water, it produces sulfuric acid. And this sulfuric acid is the most important component of acid rain. It eats away the stonework, it kills marine life, it kills freshwater life, it causes skin infections and a wide array of bad stuff which shouldn't be happening. So the conversion of sulfur dioxide to sulfur trioxide in atmosphere, it is catalyzed by oxides of nitrogen. So one of the very important things that we try to do is that see, this is the reason why we try to purify the fossil fuels from sulfur. Why? Because if we do not purify, sulfur is gonna burn in our engines as well, and it will produce a lot of sulfur dioxide, and this sulfur dioxide is then gonna cause a lot of environmental problems which none of us want. So now let's come to the contact process. So the first step in contact process is the first reaction is the reaction of sulfur with oxygen to form sulfur dioxide. Right. Now, this sulfur dioxide is going to serve as the reactant for the next step. But before we can move into the next step, this sulfur dioxide has to be purified and cleaned and dried. So what are the major impurities that will be present in sulfur dioxide? The answer is dust particles. And since we also have to dry it, it means that another important impurity is water molecules. So how is this done? If I have this sulfur dioxide here, I first pass it through a device called the electrostatic dust precipitator. You would have studied about the electrostatic dust precipitator in O-level physics. This electrostatic dust precipitator is a very important application of static electricity. So electrostatic dust precipitator precipitates out all the dust. So the dust particles exit here. Now, how do we dry the gas? What we do now is that sulfur dioxide is passed through a shower of concentrated sulfuric acid itself. Right, so this is a shower of concentrated sulfuric acid. Remember this, that concentrated sulfuric acid is a very powerful drying agent. So, when sulfur dioxide, which has some moisture in it, passes through this shower of concentrated sulfuric acid, the water molecules present in along with the sulfur dioxide, they are removed by this shower. And what leaves this shower is dry, pure sulfur dioxide. The reason that we need this dry and pure sulfur dioxide is the same as the reason behind purifying nitrogen and hydrogen in the Haber process. That is, the step that's going to follow is a catalytic step. And if we use impure sulfur dioxide, the catalyst will be poisoned and it will not remain fit for use later on. So this is done to avoid poisoning the catalyst. Now sulfur dioxide is sent to for the second step. And the second step is basically the most important step of this reaction. So if you are ever asked to write the equation of the contact process, the equation of contact process is SO2 plus O2 gives us SO3. This is a reversible reaction and this uses a catalyst called vanadium 5 oxide. Vanadium 5 oxide catalyst is used. So what's done is that we have four interconnected beds. Sulfur dioxide enters here. Each of these chambers contains beads of vanadium 5 oxide. Right, the same is present here, the same is present here, the same is present here. We need a high temperature of 450 degrees Celsius, which is the same as the temperature of Haber process. and we need a high pressure as well. But the pressure requirement here is 1/100th of the pressure requirements of the Haber process. In Haber process, we needed 200 atmosphere pressure. Here, we need a pressure of 2 atmospheres only. Right? So, after passing through all these beds, we get sulfur trioxide. Again, it is not a reaction having 100% yield, so the remainder of the gases is sent back to the converter and gases are recycled. So now we have obtained sulfur trioxide. Fine. Now, we saw above that sulfur trioxide, when it combines with water, it forms sulfuric acid. This means that sulfur trioxide is an anhydride of sulfuric acid. That means if we add water to sulfur trioxide, we are going to get sulfuric acid. But the problem is that things are not as simple as this. But if you write the conditions on this arrow as well, and you can copy this equation down. We need 450 degrees Celsius temperature and 2 atmospheric pressure. Now remember, in this equation as well, 450 degrees centigrade is a compromised temperature, and the reason why we need a higher pressure is again the same. See, we have 1.5 molecules of gas here, 1 SO2 and half oxygen, so that's 1.5, and we have 1 SO3 here. If I can write this equation as 2, 1 and 2. So we have 3 volumes of gas here and 2 volumes of gas here. So a high pressure favors the side of the decreased number of molecules of gas, and therefore sulfur trioxide is obtained. Now let's talk about the limitation and why we can't directly add water to sulfur trioxide. The answer is that the reaction between water and sulfur trioxide is extremely violent, and this extremely violent reaction produces a very fine mist containing very small droplets of very concentrated sulfuric acid, which are very difficult to deal with, right? So now let's write some stuff down. Whatever we have discussed so far, we'll write it here. In the first step, sulfur is burned in oxygen to form sulfur dioxide. Right. Sulfur dioxide is purified by removing dust particles using an electrostatic dust precipitator, and dried by passing sulfur dioxide through a shower of concentrated sulfuric acid. And why is this so? Because concentrated sulfuric acid is a powerful drying agent and dries all the water molecules that may have come along with the sulfur dioxide. This purification is necessary to avoid poisoning the catalyst. Number 3. Sulfur dioxide is now reacted with more oxygen in the presence of a catalyst, which is vanadium 5 oxide. The formula is given above. V2O5 is the formula. Right, sulfur dioxide is now reacted with more oxygen in the presence of a catalyst at 450 degrees Celsius and 2 atmospheric pressure. This produces, okay, since it is a reversible reaction, or no, we will write this down. This produces sulfur trioxide. Since it is a reversible reaction, sulfur trioxide tends to convert back into sulfur dioxide and oxygen. To avoid this, sulfur dioxide and oxygen mixture, oxygen, are passed over 4 beds of catalyst, with each bed having the same temperature and pressure conditions. Now we'll write down higher pressure is needed to shift the equilibrium in favor of the forward reaction, whereas a temperature of 450 degrees Celsius is used as a compromise. Why? Because again, the reaction between sulfur dioxide and oxygen is an exothermic reaction. Now, number 4. Sulfur trioxide is an anhydride of sulfuric acid, meaning that if both are mixed, meaning if water is added to sulfur trioxide, sulfuric acid is obtained. However, the reaction between sulfur trioxide and water is extremely violent and produces a fine mist containing very small droplets of very concentrated sulfuric acid, which are very difficult to deal with. Therefore, a roundabout method is used. A roundabout method is used to obtain sulfuric acid from sulfur trioxide. What do? We, instead of adding sulfur trioxide to water, we add sulfur trioxide to concentrated sulfuric acid itself, right? This forms a very thick viscous liquid called oleum, and the formula of oleum is H2S2O7. So what we have done is we have just added the two together. This is called oleum. Oleum is also called fuming sulfuric acid. And since, as I just said, it's a very viscous, thick liquid which has an oil-like constituency, it is also called oil of vitriol, right? So now, once we have obtained oleum, what we will now do is that we will add water to oleum. Water is added to oleum, and this gives us normal sulfuric acid. What's the reaction that takes place? Let's see. We have H2S2O7 plus H2O, and this has to give us two molecules of H2SO4. Right. So let's write this down as well. So, number 5. Sulfur trioxide is added to concentrated sulfuric acid, giving us a viscous liquid called oleum or fuming sulfuric acid. Since it is a viscous liquid with an oil-like constituency, it is also called oil of vitriol, with vitriol being Latin or something for sulfur. Right? Water is then added to oleum, giving us concentrated sulfuric acid. That's it. That's all about the process giving us sulfuric acid. So now we have obtained sulfuric acid. It's now going to be shipped to the different industries, and where they'll be using it for whatever purposes. Sulfuric acid is also used to make fertilizers. It is used to make paints. It is used in battery water. The batteries that we have in our cars, that uses sulfuric acid. It's dilute sulfuric acid, but it's used. Also, sulfuric acid is used to remove impurities from metals. See, what happens is that if I have a metal piece, many a times what happens is that this metal gets coated with an oxide layer. So, if I want to electroplate this metal, I first have to get rid of this oxide layer. And this oxide layer is removed by reacting it with sulfuric acid, with dilute sulfuric acid. And this removal is called pickling. So sulfuric acid is also used for pickling. I just recalled one thing which I forgot to tell earlier on. Sulfur dioxide has one very important use, sulfur dioxide here. One very important use of sulfur dioxide is that it is used as a food preservative. We introduce sulfur dioxide in very controlled quantities in canned food to kill any bacteria and microorganisms that might be present. Right. Now let's talk about some properties of sulfuric acid. We'll talk about only a few properties here, namely concentrated sulfuric acid is a very powerful drying agent, and it is also a very powerful uh, dehydrating agent. Now, what is the difference between a drying agent and a dehydrating agent? A drying agent is something which is gonna remove, which is gonna strip something of its water clearly. For example, when we studied it here, we had water, we had sulfur dioxide, and we had water molecules with it. This shower of concentrated sulfuric acid dried that water. Similarly, if I have uh, copper sulfate crystals have a formula CuSO4, and this is combined with 5 molecules of water. These 5 molecules of water are called the water of crystallization, and this water is essential, and these 5 molecules of water are essential to give this copper sulfate a crystal-like appearance. Now, if I put these crystals of copper sulfate in concentrated sulfuric acid, this water is going to be removed, and we'll just be left with a white powder of copper sulfate. So this again is drying. In dehydrating agents, what happens is that we don't really have water. Instead, it makes water, it rearranges the molecules of that substance, makes water out of that rearrangement, and then removes it. For example, uh, glucose C6H12O6. We can see there is no water here. But if we add concentrated sulfuric acid to glucose, what will happen is that this concentrated acid is gonna rearrange these hydrogens and make 6 water molecules from them and then dry them. As a result, only 6 atoms of carbon are going to be left. I have a nice picture here with me, and I'll show that to you. Okay, here comes this picture. So here I have a solution of glucose. I add sulfuric acid to it, and this is what's left. Why? Because this concentrated sulfuric acid rearranged the molecules of glucose, and what it did was it rearranged the hydrogens and oxygens in that glucose, made them into water, and removed them. So only carbon is left, and we can see this nice big uh, this foamy carbon appearance here. So this is dehydration. So concentrated sulfuric acid is a very important drying agent and a very important dehydrating agent. It's also used in production of acid salts. Now, what is an acid salt? A normal salt, when you dissolve a normal salt in water, more or less it gives you a neutral solution. For example, we have sodium sulfate. If I dissolve sodium sulfate in water, I'm going to get an aqueous solution of sodium sulfate, and it's going to be neutral, right? However, when sodium sulfate is formed by a reaction between NaOH and sulfuric acid with either sodium hydroxide in excess or both of them in equal amount, in according to the stoichiometric ratio. Uh, I'm not going to the details of that. But if sulfuric acid is in excess, that means sulfuric acid is present more than what is required to neutralize NaOH. What happens is that instead of sodium sulfate, we get sodium hydrogen sulfate. This is an acid salt, meaning that if we dissolve sodium hydrogen sulfate in water, we are not going to get a neutral solution. Instead, we will get an acidic solution. The other properties and uses of sulfuric acid are written very well in your book, Prescott. You can go through those uses, and if there are any confusions, we can discuss those in the class. So we are now done with with the formation of ammonia and the formation of sulfuric acid. That was the contact process. Now there's one very interesting thing that I forgot to point out. Uh, in contact process, the end product is sulfuric acid. And the interesting thing is that sulfuric acid, which is the end product of this reaction, is used as a reactant in two steps of the process as well. Where, number one, when it was used as a drying agent in the second step, and number two, when it was used in uh, to form olein. So this is the only reaction where the final product is used not once but twice to give us the final product itself. So that's all about these two processes. I hope this is very clear. If there's any confusion, we can discuss this in the class. Till then, Assalamu alaikum.